Hey everybody. In the second lesson of related rates, we're going to take a look at related rates questions in a sort of a geometric context. So in the set of examples that I'll be going over, you will see, well, in this case, you'll see areas of circles, you'll look at volumes of cones, you'll look at perimeters of equilateral triangles, and so there's definitely a geometry feel to each of these. Okay, so let's take a look at example 1. When a small pebble is dropped in a pool of still water, it produces a circular wave that travels outward at a constant speed of 15 centimeters per second. At what rate is the area inside the wave increasing when the area is 400 pi square centimeters? Okay, so we've got a diagram here that shows you at the start, after, say, the pebble is dropped into the pond or the pool, and it starts to grow, and then after a few seconds it grows more and more. So I just wanted to show you a video of this so that you can get this in your head. That's more than a little pebble, that's a fairly large rock. Okay, and there are little tiny ripples that are created, but the main ripple you can see is spreading from the center. And you can imagine, maybe that's that circle there represented by the ripple is really increasing at a rate of, say, 15 centimeters per second. Okay. So how do we approach this problem? Well, really we approach it in the same sort of way. Let me just stop that there. We approach it in the same sort of way as we did in lesson 1 of related rates. So what we need to do is come up with a diagram, and I think this suffices for a diagram. And then after the diagram, what we want to do is come up with an equation that relates the quantities that are figuring into this problem. So the quantities here are definitely, I can see that there's area involved, and well, something about the increase in the size of the wave. And what we can use here is we could use radius, right? So for example, the area of a circle can be given by a equals pi r squared. Okay, so diagram, equation. Now the next step is to come up with the derivative of this formula or this equation. And then after that, we substitute our known values into the related rates equation, and away we go. So the derivative of area with respect to time is equal to, now pi is a constant, so that stays there. We'll take the derivative of r squared, so that would be 2r dr dt, right? Again, chain rule has us go back in and take the derivative of r with respect to t. So there it is. That's the related rates equation. And now we just want to know at a particular moment in time, what is the rate of change of the area? Okay. So obviously dA dt is what we're looking for. 2 pi, we don't need anything there. The radius, we don't know. But we do know that at that particular moment in time, the area is 400 pi square centimeters. So I'm going to take this formula that we have, a equals pi r squared. I'll sub in 400 pi square centimeters and solve for r. Okay, so the pi's cancel, and then the square root of 400 is equal to r, and r is equal to 20 centimeters. Okay, so then over here, I can just go dA dt is equal to 2 times pi times the radius of 20 centimeters times the rate of change of the radius, which we can assume is the 15 square centimeters. Sorry, not 15 square centimeters, 15 centimeters. And my final answer is going to be equal to, well, let's see, I think that's going to be 600 pi square centimeters per second, right? Because it's 15 centimeters per second, so that per second stays. And there it is.